Hello, this video is about the Doppler effect. Now, you know the Doppler effect even if you didn't know what it was called. That's when a police car or a fire engine goes by, an ambulance, and it's got its siren, and then as it's coming towards you, it sounds like one thing, and then once it passes, it sounds like another. And so, this is the Doppler effect. It's the pitch, the frequency of a noise that changes because that source of sound is either moving towards you or away from you. So imagine we have just a source of sound, speaker, sure, we'll call it a speaker, and it's emitting sound. We can talk about the waves it's emitting. So you can imagine the waves going out, and each of these circles is represents the peak of one of those waves. So you can say it's, can I do this? Down, up, down, up, down, up. Not very good. But each of these circles represents the peak of the wave as those waves are moving out. They're also called wave fronts. So for a source of sound that's moving, it's just, this is what we've got. We've got a nice constant ring of circles, and the waves are just moving along. But what if that sound, that source of sound is moving? What would happen if we have the source of sound moving to the right? I'd like you to think about this and predict what would these circles now look like? How would these change, move, whatever, if that source of sound were moving to the right? So this wavefront right here, if you think about it, this was emitted first, and then this was emitted next, and then this one, and then this one. And so, you know, we've got a wave that's being emitted, but then the source goes bloop, and then we've got another wave being emitted. Source goes bloop. So make a prediction and see what kind of circles you think you would get. Okay, got your prediction? What we have is, this is, I'm not good at drawing this stuff. I need to get a little more practice. So if we have that first, the most recently emitted wave front, well, the one right next to it, the one that was emitted a little bit ago, was actually emitted when the source of sound was back here. And the one emitted prior to that is emitted when the source of sound was right here. And so what happens is these wave fronts, these peaks of the waves fronts get squished up here and they get expanded, spread out back here. Now remember that these circles are all representing the peak of the wave. Each of these is the peak of a wave. So peak, down, peak, down, peak, down, peak. Something like that. How does the wavelength of this wave compare to the wavelength of that one? And remember, wavelength is from peak to peak. So it's really the distance between the lines. So here, the lines are much closer together than they were originally. And so out front here, the wavelength is lower than when it was just holding still, because those wave fronts get squished together. And back here, the wavelength is bigger because they get spread out. So the distance between the circles is bigger. So what we have is the wavelength changing as the source is moving. So for a source moving towards an observer, if somebody is standing here, what they have, the waves that hit them have a lower than normal wavelength. But if we remember how wavelength and frequency are related, they're related by the wave speed. Now the wave speed is just speed of sound in air, so this stays the same. So if this goes down, what has to happen to the frequency? The frequency needs to go up. And if you want some numbers, we could do 16 equals 4 by 4. So if the wavelength goes down to 2, what does the frequency have to do? Well, 16 is 2 times what? It's 8. Frequency's got to go up. So when the source of sound is moving towards an observer, the frequency goes up, if the observer is standing back here and the source of sound is moving away from them, the frequency goes down. And this is what you hear when you are hearing the Doppler effect. It's pitched high when it's coming towards you, but as soon as it goes past you, it drops down. Near. And that's what you should be hearing when you have a good source of sound passing by. So that's the basics of a moving source of sound. The other thing we can do is we can get the Doppler effect by having a moving observer. So that's next. Okay, so the other way we can do it, moving observer. So let's say we have a source of sound, and now the observer is moving towards the source of sound. So we're on a skateboard, and let's say we're moving that way. Now what do the wavefronts look like for this source of sound? It's not moving, so what we've got is just those nice concentric circles at their regular spacing. And what happens as that observer moves towards the source of sound? Well, if they were just standing here, the waves would hit them doot, 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 doot. But now they're moving towards them. How frequently are they hitting those wavefronts? Doot, 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 doot. So it's more frequent because they're moving towards those wavefronts, and so they encounter those peaks of the waves, those wavefronts, more frequently. More frequently. Higher frequency. So for here, if we're moving towards the source of sound, we hear a higher frequency. But not because the wavelength has changed. This is one of the cool, weird things. The physics is different for a moving source and for a moving observer. So for a moving source, the wavelength changes, and that means the frequency changes. For a moving observer, it's just that we're hitting those waves more frequently. And so if we were standing, they would just be coming at us, bing, 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 bing. But when we move towards them, it's bing, 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 so we hear higher pitch. And likewise, if we are moving away from the source, don't you like my skateboard? Then we are encountering those wavefronts less frequently. We're kind of running away from them. And so here the frequency goes down. The pattern you hear is the same. Moving towards, higher, moving away, lower. But the physics is slightly different. And so with the Doppler effect, it's just this kind of cool thing about the way the waves interact with a moving source or a moving observer. The other thing you should know is what can we do to change how much that frequency changes by. So what could we do to get a higher change? So instead of, if this is the note, and it goes, how can we go from to So what could we do to get a bigger change? Make a prediction. What do you think we could change about a situation to get a higher change in frequency? All right. So you may have said speed. And if you said speed, you are right. So the change in frequency, and this delta sign means change. So that triangle is our shorthand for the word change. The change in frequency, it depends on actually two things. It depends on the speed of either the observer or the source, and it actually depends on the original source frequency. So a higher note to start with is going to have a higher change than a lower note. So if we had a low siren, something starting, that's low for me, that would have less change in frequency, either higher or lower, than a real high note, which is, again, one of the reasons that it's more noticeable. The Doppler effect is more noticeable with sirens. They tend to be pretty high to start with. And so that is just the overview of the Doppler effect. And you know the Doppler effect. Now you can go listen for it and say, okay, what's happening? I think since the source is moving, the wavelengths coming at me are more frequent, so the frequency goes up, I hear a higher pitch. I'm sure you'll do that next time you hear about next time you notice the Doppler effect. All right, good job for watching.